Alright, we'll go over the other ones in the packet. I gave you maybe 3 more, and then I have an extra one today with more of the drawing practice. So this is for y'all to have some stuff in your notebook, excuse me, with some slope fields worked the right way. First one I'm going to do is 2000, number 6. Yep, 6. 2000, number 6. If you're looking at your little packets, I've marked out the 2 above it because I think you've either done those or they don't apply to what we're doing. Number 6 is the only one that's the differential equation. So here's where they start. Is we've got dy dx is equal to 3x squared over e to the 2y. Alright, this was a non-calculator question. I think most of these will tend to be non-calculator. It kind of defeats the purpose of having the slope field, because there are programs out there you can put on your calculator that will draw slope fields for you. You put in the equation and give it a window and it'll do all the little tick marks for you. It's a 2-parter, so I'm thinking point-wise this was pretty big, either like 3-6 or 4-5, you know, big point-wise there. Part A, find a solution y equals f of x to the differential equation satisfying the condition that f of 0 is equal to a half. Alright, so we'll need this to help us find our plus c. I'm banking on this being the big point question, since it's the one where we're finding the equation, either 5 or 6 points out of this. So separate the variables first. That's going to give us e to the 2y dy is equal to 3x squared dx. Right? Antiderivative of each side. That's going to be a teeny tiny u sub, and this is the kind of u sub you should be doing in your head. U would be 2y, so du would be 2 dy. We'll bring the 1/2 over. So I'm going to get 1/2 e to the 2y. This is going to be a good old x cubed, and then I'll tack on my plus c. Notice at this point, we're up to 4 points. And that's a quick and easy 4 points in under a minute. Separate the variables, 2 antiderivatives, and then the plus c. The last 2 points I would probably get from using my initial condition and then solving. So I'm going to go ahead right now and figure out what c is. This is an x value of 0 and a y value of a half. That's convenient. So to find c, I'm going to have 1/2 e to the 2 times a half is equal to 0 cubed plus c. That's gone. That is e. So c is going to be 1/2 e, or e over 2. All right. That gives us, where are we? Okay. That gives us the equation. Let's scoot up here. 1/2 e to the 2y is equal to x cubed plus 1/2 e. Okay, we're up to 5 points now. So I'm thinking for the last point, let's just get y by itself, which isn't too terribly rough. I multiply everything by 2 first, so e to the 2y is equal to 2x cubed plus e. Take the natural log of both sides, so we get 2y is equal to the natural log of 2x cubed plus e. Probably need to do this until I figure out what's wrong. And then y is going to be equal to 1/2 natural log absolute value of 2x cubed plus e. Contrary to popular belief, this natural log will not cancel that e because it's not isolated. We need the natural log of e all by itself in order to do that. And I think if we're going through the point 0, 1/2, the natural log, or the absolute value will be unnecessary, but I'm not going to chance it. Do that. All right, part B. Find the domain and range of the function f found in part A.
Domain and range?
Yep, domain and range.
Well, nothing's bad.
Well, hang on. This is where I really need to go back and look at my absolute value argument and see if we're okay on this. But the way we've got it written with the absolute value, the
Anything
domain's
works.
gonna be all reals. If it's not absolute value, I don't think the absolute values are, yeah, I don't think we're supposed to have them. That. Okay, let's see, domain. Well, for the domain, we need this part right here to be positive. So whenever 2x cubed plus e is positive or greater than 0, that means 2x cubed is greater than negative e. Means x cubed is greater than negative e over 2. So x is going to be greater than the cube root of negative e over 2. That negative could be pulled outside if we wanted to. Pretty good setup there. All right, range.
The range of that,
Yep.
um,
Well, here's the thing. The natural log by its very nature is an increasing function. It's going to be going up, especially if our values of x are getting bigger and
Yeah.
bigger. So we basically need to know where this bad boy starts, I guess. I'm feeling like it's going to be negative infinity, or all real numbers, because the natural log has an asymptote and it drops
so
like
wait,
that.
we took off the absolute value?
Yeah,
Okay.
I'm still not sure if, well,
Cause aren't we supposed to always just have it in there, and the reason we do it is so it's always safe, and so if they want to, don't.
here's my argument though, here's the thing. When this is always going to be positive.
Mhm.
There are certain values that I can't plug in for x right here. Okay, if I put the absolute value on, then it actually includes a whole lot of numbers that we should not be including. It includes all these negatives that we can't get out of this function right here, or this thing, not necessarily a function, but this thing right here. It is a function. Look at this, okay, the e part has to be positive.
Mhm.
That has to be positive. If I start slapping absolute values on this, then it takes a lot of these negative answers that would not work here, and it makes them work here.
Okay.
That's why I'm saying we have to restrict it, because we need this part over here to actually be positive.
So you want to restrict.
So we needed to restrict this one. The range though is what's getting me, because I don't think this one has,
An easy.
no, I think it's easy. I think it's, the natural log looks like this,
Yeah, it's just a.
which has a range of all real numbers, because it hits its asymptote all the way down, it goes up that way.
It really doesn't matter what the number is.
And it doesn't matter what numbers you stick in for x. If we, as long as we're using numbers like this, it's gonna be pushing us. I'm gonna say range on this one is all reals. Don't quote me on that, but I'm pretty sure. Let me go with that. All right, it's 2006. Let's look at the next one. 2000, I'm sorry, not 2006, 2000 number 6. So now let's do 2001 number 6. Number 6. All right. F is a differentiable function. You have the point 3 1/4. Okay. given to me. And the slope at each point is given by dy dx is equal to y squared, and then 6 minus 2x. Okay, again, a two-parter, I'm thinking, yeah, first part's probably 3, second part's probably 6 or 4, 5. Part A, find the second derivative and evaluate it at 3, 1/4. Okay, part A.
So take a derivative.
Take a derivative of that. So, second derivative. Gonna be a product rule. I'll keep the first, derivative of the second, plus keep the second, derivative of the first. That's implicit, so we have to go, if we're doing it with respect to x, we have to do that. We could clean it up, could.
There's no reason you have to.
We're getting ready to plug in the numbers 3 and 1/4, so you can spend the time cleaning it up or do the arithmetic, it doesn't matter. So second derivative of y with respect to the second x at the point 3, 1/4. All right, here we go.
Y would be 1/4 squared, 2, 6 minus 2,
times 3, is that right?
yep, and then 2, 1/4. Then we have to bring in that.
Okay.
Yep.
Well, let's just do this. Over here, dy dx at the point 3, 1/4 is gonna be 1/4 squared times 6 minus
2.
2 times 3. All right, so we're gonna, well, it's gonna be 0. 6 minus 6 is gonna be 0, that gets knocked out. So this will be times 0, which is actually rather convenient
Because the whole
because
side gets wiped out.
this whole second half gets knocked out, so we're
it's
looking
really
at
just 1/8.
negative 1/8.
So, yeah, negative 1/8, negative 1/4. Oh no, that's 6, never mind,
Is that right?
1/8, 1/8.
Okay. So my answer for that one's gonna be negative 1/8.
Damn,
Yeah.
easy,
Thank you.
easy.
All right, part B, find a particular solution that goes through that. All right, so here we go. Separation of variables again. Let's see, I'm gonna divide by y squared, so dy over y squared. And I'll bring the dx to the other side and get 6 minus 2x dx. Two antiderivatives. That is not natural log. Some of y'all try to force every single fraction you see to become a natural log. It is not. It's going to be negative 1/y. This side is going to be 6x minus x squared plus c. Again, nice 4 points right there. Let me get comfy. Let's find c.
Okay, so
Negative 1/4. That's nice.
that's 4.
6, was it 3? Yeah. 3 minus 3 squared plus c. So we're gonna get
Negative 4.
4 equals
18.
18 minus 9, so 9 plus c. C equals negative 13. 13. All right. So that gives us negative 1/y equals 6x minus x squared minus 13. All right, the negative is easy to take care of. I'm going to rearrange that, that's irritating me. 1/y is equal to x squared minus 6x plus 13.
Yeah.
Everybody cool?
And
And then I'll reciprocate it, so y is going to be 1/x
that whole thing.
squared minus 6x plus 13.
I also love how you can just switch things.
I know, beautiful.
It's like,
Oh, little knees.
getting old.
Yeah. I think if we do stick in 3, you get 9. Minus 18 is negative 9 and 4, so there's your 1/4. Beautiful, it checks out. Ta-da! Yeah, you got 15 minutes on each of these. but these should not be 15-minute questions. This should be where you're kind of banking extra minutes.
That should have been 8 minutes. Oh, well, that, one of them should be like, yeah, around 8 minutes.
All right, 2003B, number 6. Notice how we get a lot of number 6s.
Let's be number 6. Don't judge.
It is, I don't think I've ever seen it in recent memory where it wasn't on the non-calculator, so it's always on the back half. 2003B. 3B, number 6. Okay. Let f be the function defined by f prime of x equals x square root of f prime of f of x. Okay. Where f of 3 equals 25. There it is. Okay. Part A. Find f double prime of 3.
Okay.
All right, so first thing we have to do is find f double prime of x, and then we'll just stick in, stick in.
Don't fall.
I know, right? Stick in 3 for that.
Nice, the old, product,
Product rule and
chain.
rule, yeah.
Or is that, that's,
No, it's
Oh,
chain
yeah.
because we
That's
have
fine.
all xe things in there. You can turn that to y if you want to, which is what we'll have to do in part B, I think. So I will, let's see, derivative of the first is 1, keep the second, plus,
you go first.
keep the first,
Derivative the second, so
derivative of the second, which is gonna be 1/2
thing squared.
f of x to the negative 1/2.
Yeah, negative.
Then we'll chain the inside and get f prime of x.
Which is just y and then d right here.
Right, yeah. So now if we want to do f double prime of 3. Okay, so let's see here, that is going to be the square root of f of 3, that's convenient, plus 3/2 times f of 3 squared, I'm sorry, to the negative 1/2, which will pull it to the bottom, times f prime of 3. Okay. F of 3 is 25, root of 25 is 5. 3/2. Okay. F of 3 is still 25, but it's kicked to the bottom now, so 1/5 there. Okay, times f prime of 3. F prime of 3 is going to be 3 times the square root of 25, so 3 times 5 is 15. Everybody see how we got that? Plug this f of 3 back in, or f prime of 3 back in here. Okay, let's see. 9/2, 5 plus 9 halves, I think. 10, 19 halves. Sounds good. Alright. F double prime of 3 is 19 halves. A lot of arithmetic. You did have to do product rule, which a lot of people forget, with a little chain in there. Okay, part B, write an expression for y equals f of x by solving this differential equation. dy dx equals x square root of y. So that's really what they've done, is called this the original y value. So you have x's and y's in it, with the initial condition that f of 3 is still equal to 25. You know, they really wouldn't have to tell you to do this. I mean, they're kind of hinting that's what you need to do, but you honestly should have been able to figure it out. Okay, let's separate it. We've got dy over square root of y equals x dx. Again, not natural log. Antiderivative, antiderivative. Okay, that is y to the 1/2, or negative 1/2, excuse me. So raise the power, we get a half, so this is going to be 2y to the 1/2 is equal to 1/2 x squared plus c. My initial condition is that f of 3 is 25, so I'll plug in 25. 2 square root of 25 is equal to 1/2 times 3 squared plus c. 5 times 2 is 10. 10 equals 9/2 plus c. The c equals 11/2, I think. That's 20/2 minus 9/2, 11/2. So we are at 2 root of y is equal to 1/2 x squared plus 11/2. Okay, it's irritating, but we actually have to divide by 2, so the square root of y is going to equal 1/4 x squared plus 11/4, or if you really want to at this point, you can do this, x squared plus 11/4. Don't know if it helps or hurts you, whatever.
I like that.
And then we'll square both sides, so y is going to equal x squared plus 11/4 quantity squared.
So I just realized that, I don't know if you said it or not, but really, we're just taking the antiderivatives of implicit problems.
Correct. Yes.
Really,
That's all slope field. You can do them with stuff that's explicit, with just x's, but it's the same crap
Well, I
we've
mean,
been
like-
doing from the day one.
It's just the splitting the variables is just like, we're just.
And you'll notice all of our slope fields, even though we haven't drawn big ones, they do kind of look like they're starting to curve and twist all over themselves. They have these weird shapes. But yes, this is used to help us to take antiderivatives of usually implicit problems. Yep. Good stuff. All right, 2003B number 6. I think that is all from the packet that I gave you. And I have one extra one because we haven't had the graphing examples. So we'll pull
That's a good problem. I like the.
this one. This
D
one's
on
awesome.
some.
D is, I
That's
think we got it
fine.
right. It's a hard one. It's
No,
not all
I didn't get it
reals.
right.
Yeah.
I didn't get it right.
Huh?
I didn't get it right. No, it's actually,
It's got a little something on it.
good idea, thanks. It's actually, that's the answer. That would be the answer.
The worksheet, if you'll notice, I don't know if y'all read it at the top, this is 2000, number 6, from the BC test. Okay, this is a BC topic. Like I said yesterday, before, this is one of those in the gray area that a long time ago it used to be in the BC, and then they switched it over to an AB topic. So this was a year that it happened to be a BC topic only and not an AB topic, but we can do it now. It's the same kind of question we do now. So here's where they start us. Consider the differential equation where dy dx is equal to x times y minus 1 squared. Part A, draw with the dots. Got it. Draw the slope field with the dots. Okay, this goes,
And this would be actually, what is it, it's this function called?
I don't know.
It's like the double, it's the two asymptotes, but they're both at the bottom. It's not 1 over x, but it's the,
2 asymptotes?
It's-
You mean from the picture you drew?
yeah, that's what, what this is showing is that it's probably going to be it's two asymptotes going at the bottom, is what it looks like.
Ooh, that's kinda cool.
Well, at least that's
Alright.
what it looks like. With the-
0, 0, we get 0, I think. Yeah, 0 for x, and then y. Get that, alright. 0, 1, actually, anything with a 0 for the x is gonna be 0. And anything with y1 is gonna be 0 as well. Okay? 1, 0 is gonna give us, alright, let's see, 1, 0, that's gonna be 1, so a slope of 1. Negative 1, 0 is gonna be a slope of negative 1. 1, negative 1, okay. That is, negative 1 is negative 2 squared is 4, so this is gonna be a positive 4. Just make it look really steep. And then this one I think is gonna be negative 4. Make him look really steep. Alright, There's your slope field.
No, my OCD just
Which-
kills me on these.
Which is why I think it's the, I don't know, which the one where it's just the two it's the two asymptotes on the bottom with that type of function.
Two asymptotes on the bottom.
Yeah, like this, and then just have the two asymptotes like that. Not the
Oh,
asymptote.
you have a vertical asymptote, and those aren't asymptotes, but you have, that's like 1/x².
That's what.
That's technically negative 1/x² because it's upside down, but yeah.
That's what that.
It's gotta vary that feel, except for the fact that you actually have points here.
Yeah,
I'm thinking more something like this,
yeah.
something like that, and then the further down you go, the more steeply it dips and then comes back up that way, that's what I'm feeling. And the part we don't see, which I think is pretty cool, is up here. Because if it's gonna, I'm picturing bubbles, I'm picturing asymptote, and then I'm picturing a dip bubble like that, and it's probably the same on the top end if we were to plug in numbers like that. They haven't asked us to, but it probably looks like that.
Number B, I don't know exactly how to do it.
Okay, this was worth 1 point. I'm pretty sure it's only worth 1 point. Use the slope field of the given equation, so that,
To say what
to explain why that picture cannot be,
It
the
goes really
original
far
one.
above one, which it's supposed to be blocked off pretty much at one.
yeah. Now, what I don't know is whether or not it's an asymptote. I think it is, except for this one right here. If you were to actually plug in y equals, you would get a horizontal line right here, and the rest of the graphs would do that bubble thing. So the reason that that picture clearly cannot work is because when y is equal to 1, I'm supposed to have horizontal tangents, and that one does not. Okay? So for part B, when y
Yeah, you're
equals
supposed to have
1,
an
you're
asymptote.
supposed to have a
Yeah.
horizontal, it's either gonna be a horizontal line or horizontal tangents across there. F of x should have horizontal tangents. And this graph clearly does not.
Yep, because it's, when you do number 3, it comes up to like -2 over x squared plus 2.
Yeah, so
And it has
weird.
the plus 1 on the outside, so that's why it's
It's
above.
up 1, yeah, cool. All right, find the particular solution to the given differential equation with the initial condition, all right, here we go, initial condition f of 0 equals -1. So here's our dy dx, and we're gonna use the initial condition that f of 0 equals -1?
Yeah.
-1. All right, rock and roll. Separate the variables, we're going to get dy over y minus 1 squared is equal to x dx, not natural log. It is a u sub, however.
I was thinking like tangent maybe, and it's like, no, it's
Yeah.
not.
If you let u be y minus 1, you get du equals dy, so it's a straight swap out. You end up getting, for this side,
Negative
1 over
y
u
minus-
squared. Okay? Which is u to the -2, which is -1 over u, which is -1 over y minus 1. So if we were to crunch through the du and all that kind of stuff, we get that. This side's pretty easy, 1/2 x squared, and then the plus c. All right, so now let's find our c value using that condition. So when x is 0, y is -1. We're gonna get -1 over -1 minus 1 equals 1/2 0 squared plus c, gone. This is gonna be positive 1/2 equals c, oh, there you go, equals c. So -1 over y minus 1 equals 1/2 x squared plus 1/2. I like it, I think. Or, do this. Since both of these are over 2, we could say x squared plus 1 over 2.
Mhm.
Kind of nice. All right, I'm gonna do two steps in one here. I'm gonna reciprocate it, both sides, and I'm gonna multiply by -1. So I'll get y minus 1 is equal to -2 over x squared plus 1. That was, again, flipping both sides, reciprocating, and going ahead and multiply both sides by -1.
And then plus the one.
And then bring the 1 over, so we get y equals 1 minus 2 over x squared plus 1. There we go. Part D. Find the range. Okay,
Pretty. Well,
this one's, this is kinda rough.
we know the asymptote.
You what?
We know that there has to be an asymptote.
Why?
Well, because, you put it to infinity, just put it to infinity. Bam.
Okay.
Handy dandy rule.
Thank you. Handy dandy rule would tell me there is an asymptote at y equals
1.
1. Very
And
good.
it's 1 minus.
Because this part's gonna end up being 0. So the question is, did I actually go above the asymptote and come back down, or is this one never actually going to hit 1?
Well, you should be able to go above.
This is always gonna be something. This right here, it's gonna wanna be 0, but it's not going to be 0. So
You
this
can
is
never
always
get
gonna be
above
1 minus a
something.
little bit, so you're never
Yeah.
actually going to hit 1. So on the low end, I'm sorry, on the high end, we're never gonna hit 1. What about the low end?
Uh,
Is this going to go down to negative infinity? Is it gonna stop at 0, or is it gonna stop at some other value that we have yet to determine?
You. That's not right.
What?
It's, oh yeah, it is, never mind, okay, you just wrote different, okay, yeah.
Well, not done yet.
No,
There's
you-
the other end.
No, I was looking at the just y equals.
Look at your picture.
Yes.
Okay. What's that? Well,
We don't know.
okay, a couple things going on
It can
here.
easily, oh, it can never go, wait a second, because if you plug in, the lowest it can get on the bottom is 2 minus 1, so
One minus 2.
1 minus 2, which is -1, which is your lowest point
Okay.
possible.
Right.
Because if you plug in 0 is your lowest number, because all negative numbers will be turned into positives.
Good.
So 0 is your lowest number, is your minimum value that you can actually get. So the lowest would get you minimum.
I'm 99% happy on that. We would need to justify that's a minimum by taking a derivative and setting it equal, finding critical numbers, but you're right, okay? Because of the symmetry.
Because of the symmetry. That's just because